Okay, so now we're moving into chapter 9, and we're going to talk about gases and the properties of gases and how we can define those properties, predict those properties, and things like that. And I hope chapter 8 went well. And here we go. So, properties of gases, we can talk about the pressure of a gas, we can talk about the volume of a gas, we can talk about the temperature of a gas, and then finally we can talk about the amount of a gas. So if we talk about this pressure, generally we like to work in atmospheres, but one atmosphere has multiple conversions, and so this one atmosphere allows us to look at um, either millimeters mercury, torr, bar, or kilopascals. And so what you don't see here is that this is converting one atmosphere, or it's converting from atmospheres to kilopascals. So that conversion relatively easily. So these particles are so small, right? How on earth, literally, do they exert pressure? Well, they are particles, right? And so I'm recording this here in Denver, Colorado, and so I'm at a mile high, and at a mile high, there's not as many particles, and so the atmospheric pressure is a little bit lower. As you're viewing this, you're probably somewhere close to York, PA, or somewhere closer to sea level. And at sea level, the atmospheric pressure is generally about 1 atmosphere. And that is literally the pressure of those molecules um, pounding down on an area, right? And that is equal to 1 atmosphere. So it does depend a lot on the surface area in which the object is actually exerting that pressure. So if you look at something like this, right, and you say, well, an elephant or a figure skater, which one is exerting more pressure? And the elephant's 14,000 pounds, the figure skater only 120. Sorry, this didn't convert well. Because of the uh, size of the blade, you exert much more pressure on the surface of the ice than the elephant's foot, because the foot is much larger, and that area to allows the area to be spread out a little bit more, and so not as much pressure from the elephant's foot. Okay, if I can get to that, and I can't quite get to the bottom part of that slide. But because of let's talk about how we actually measure pressure. And the way in which we measure pressure is using something called a barometer or a manometer. And essentially, what we're looking at is we're looking at the atmospheric pressure versus the pressure inside a tube. Okay, and so if we evacuate that tube, right, and we stick it down into a vat of mercury here, that actually gets sucked up to a specific level, right? And when these two levels are exactly the same, it should be the outside. When you can put this down to the exact same level of what's in this, okay, when you get it to that exact same level, then they're equivalent. The atmospheric pressure, which is what this is signifying right here, The atmospheric pressure is exactly the same as the pressure inside the tube. And so you can also do that with something called a manometer. And the manometer, again, you've got this closed end, you pull a vacuum, you've got a certain amount of mercury in that tube and the U portion of it. And again, the pressure from this side, right, if it's higher than the pressure on this side, then it's going to push it up, and that height differential is going to tell you what the actual pressure is. Most of this is done with electronic pressure gauges now. Okay, so let's talk about the laws that kind of govern how gases behave. And you've probably heard of these before. The first one is Boyle's law, and Boyle's law talks about the relationship between pressure and volume. The rest of the measures are remaining constant, so the amount of gas and the temperature of the gas of that particular sample is going to remain constant. And then we go to Charles' law, where we talk about volume versus temperature. Again, amount and pressure remain constant, and we go to Avogadro's, where volume and the amount, the moles, are. We look at that relationship, and pressure and temperature remain constant. Okay, so let's take a look at Boyle's law. So in Boyle's law, what we have is pressure and volume are proportional, right? So this is a proportionality sign. And that proportionality says that it's 1 over volume, right? So proportional, inversely proportional. And so it's PV, right? And that equals some sort of constant. Okay? So again, the number of moles and temperature have to remain constant. And in that case, then if we change the pressure, the volume, if we increase pressure, the volume has to go down. If we decrease pressure, the volume has to go up. If we increase volume, the pressure goes down. If we decrease volume, pressure goes up. Okay? And that's what it looks like. Again, on this side, you've got the pressure and volume, the inverse proportionality. And so, again, at high pressure, volumes are lower. At low pressure, volumes are much higher. But you can also graph 1 over, right? And so if you graph pressure versus 1 over volume, you get a straight line, okay? So take a quick look at this. I'm not going to do much detail on this because we'll go over it a little bit more. Anyway, we can look at what initial pressure might be. We could be given 3 of these, right? So P1 V1 equals P2 V2. You've probably seen that before. You've probably worked that before. P1 V1 equal P2 V2 means that if we know any of the 3, if we know P1, V1, and P2, we can find V2, right? If we know V1, P2, V2, we can find P1, and that's what's happening in this problem, okay? Again, you know that temperature and the amount are remaining constant. So let's look at Charles' law, right? Charles' law, we talk about volume and temperature, and volume is directly, right? Volume is directly proportional to temperature, and so V over T equals a constant. All right, that's Charles' law. Again, the amount and pressure have to be constant. If we look at a sample and we change the the volume and look at how the temperature varies, we get a straight line. That's because of the inverse proportionality. We can look at Avogadro's law, and again, Avogadro's law is relating volume and the amount, and so it is, again, directly proportional, and so as volume changes, amount has to change, right? Volume increase, amount increases. Volume decreases, amount decreases. The final part of this we're going to look quickly at is pressure and temperature. And pressure over temperature, again, holding everything else steady, is a constant. Okay, and so as pressure changes, temperature has to change, and they're directly proportional, right? And that's Gay-Lussac's. But what we really want to look at is the ideal gas law, okay? And the ideal gas law is PV equals nRT. And a lot of this is cut off here. And when we look at this, we have a bunch of standard conditions. Standard conditions, we can use those for a variety of purposes, but standard conditions, what we want to look at is we want to look at the units, and so atmospheres, liters, moles, right, for the amount, and then Kelvin in terms of temperature. And we have to use those units, okay? And so whenever we're faced with the ideal gas law, we have to make sure that everything, pressure has to be in atmospheres, volume has to be in liters, the amount has to be in moles, and R has all of those in it, right? And then temperature is in Kelvin. So let's take a quick look at a problem using PV equal nRT. And here we've got a temperature. It says at what temperature must a 3,450 milliliter sample of oxygen be such that it contains 5.04 times 10 to the 22nd molecules under 734 millimeters of mercury. And we have to convert these things, right? So first thing to do is volume goes to liters. Moles, right? We have to take this oxygen sample in molecules, and so we use Avogadro's number, 6.022 times 10 to the 23rd, and we get the number of moles. And then finally the atmosphere, right? 734 millimeters of mercury divided by 760 millimeters of mercury in one atmosphere, and we get 0.966. Then we can plug them all in, right? So what's missing? Temperature. And we plug all these things in, and we use the ideal gas constant, which is 0.0821 liters atmosphere per mole Kelvin, right? This is a really important thing to remember. Liter atmosphere per mole Kelvin. That guides you and lets you know exactly what units you must use in the ideal gas law. The ideal gas law has a lot of different purposes. We can relate density to through the ideal gas law, and we can do that using molar mass. So if you look at density, it's mass per unit volume, right? If we plug into the ideal gas law and we plug in and get this isolated, right, we can go from density now to using the molar mass inside of this formula, right here. Okay. And then we can get to where the molar mass is now equal to the mass of that sample times RT over PV. Right? Once we know that, we can get to density component. Okay, again, back out and get density in terms of mass per unit volume. Here's nitrogen gas, right, at standard temperature and pressure. Here's the molar mass of nitrogen. Here's the molar mass in the term. Here's everything else, right? All these other at standard temperature and pressure, and there you get the density. Right? Again, we'll come back and look at these problems a little bit more in our Zoom session. So molar mass of a sample, we can go from conditions and find molar mass, right? If we know the other components of that sample. And so it says what's the molar mass of a sample of a diatomic. It has a density of 1.723 grams per liter. Again, this rearrangement where density is part of this, right? We can solve for density in this equation. Now we plug it in, and we've got this 1.723 times R times T over the pressure, right? And again, density was little m, mass, over volume, right? And so that volume term is now gone in here, right? And all we have is pressure at the bottom there. And we can come up with a molar mass of 37.95. You could look at the periodic table and figure out what diatomic that is. The combined gas law, okay? So the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. All right, what's that mean? Well, it means that there have to be some constants, right? R obviously is always constant in the ideal gas law, but that means we have to hold N constant, right? So we can't vary the amount. And in that case, as we change pressure, volume, or temperature, right, we can find out the new conditions. So what's this look like? If we have a 37.5 liter sample of helium, and initially it's in a balloon at 21.3 degrees C, 752 millimeters of mercury. Balloon rises to a new altitude, and the temperature is now minus 8.4. The pressure is only 712. What's the new volume? Okay, so again, we plug things in. Pressure is this 712 over 760. Right, so that's millimeters mercury, and this is 760 millimeters mercury per atmosphere. Right, so this is going to be P2, right? P1 is equal to 752 over 760. And then temperature, right? We have to convert these to Kelvin. And so Kelvin is 273.15 plus degrees C. And then finally, what are we looking for? We're looking for its new volume. So I have two temperatures to get to. So T1 is going to be 294.15 Kelvin. Right, and T2 is going to equal, so we're taking minus, we're going to take away 8.4, and so quick math on that, 273.15, hang on, 273.15 minus 8.4. so I get 264.75. All right, so now I've got P1, P2, T1, T2, right? And I had V1, which equaled 37.5 liters. Okay, so plug all those in. Right? That's all there is to it. We're just going to plug them all in, and once we get to the correct answer, we're there. Plug them all in, and what we get is actually 35.6 liters. Sorry, I don't have quite enough space on this page to put them all in there. Okay? So, let's keep moving. The law of partial pressures. Okay? Let's talk about that for a minute. If you take a certain gas, right, and it exerts 300 kilopascals, and you put it with two more gases, one of which exerts 600 and the other 450, they're all now exerting the pressure that they originally exerted, and so it all adds together to get to a total pressure, right, of 1,350 kilopascals. Okay? So, again, this law of partial pressures can be used to look for pressure, but it can also be used to look for the amount of a particular gas. Okay? And so the pressure that a gas exerts on the system, right, is proportional to its moles, or mole fraction, okay, times the total pressure. Mole fraction says that if I have n moles of, let's say, a gas number 1, put that over n total, the total moles of gas in a sample, and now I've got the fraction of 1. Okay? All right. Oops. So we can use it in those ways. Okay. Let me see if I can pull this together a little bit. Yeah. Okay. That's better. All right. Learning as I go here. So again, we can look at this stoichiometrically, right? And we can say, as you're conducting an experiment and you look at the combustion of ammonia, you can have all these conditions given to you, right? And you can determine the mass of NO that was produced in that sample. Okay? All right. And again, we'll save that for Zoom meeting. Let's see if we can get this one on the page. There we go. Yeah, this one doesn't actually come onto the page. We're going to skip to the next one and through this again in the Zoom session. But let's talk about the kinetic molecular theory. Okay, when we talk about the kinetic molecular theory, there are 4 postulates that we need to consider. Okay, and the 4 postulates of the kinetic molecular theory, I'm confident you've heard of the kinetic molecular theory before. Those postulates are that the volume of a gas in a sample is much smaller than the volume that that sample occupies. Those gas particles are constantly moving and moving randomly. Collisions between particles and the walls of the container are elastic. That means they don't lose any energy. And the average kinetic energy of the gas particles is proportional to the temperature. Okay? All right. So if we take a look at these different laws that we've talked about, and we look at the changes, right, as you increase the temperature, right, you have to increase the volume because the pressure that these guys are exerting is greater according to the kinetic molecular theory. As you decrease the volume, the pressure is going to increase, right? Because these guys are in a smaller space. They're still moving at the same speed, exerting more pressure, right? And then if you put more gas particles in there, you're going to increase the pressure, which then results in an increase in volume. And so that's Amonton's law, Boyle's law, and Avogadro's law. Okay. Now, again, particles moving, right? That's what the kinetic molecular theory is all about. And we talk about moving particles. We can look at the speed of those particles. And we can look at the speed of those particles according to both temperature and the size of a particular gas particle. Okay. So in a typical diagram, you're going to look at a given temperature, and so this is oxygen at 300 K, and you see the average speed, right, is right in here, and then it falls off pretty quickly, picks up pretty quickly, and you have this average velocity. Well, it should make a lot of sense that as temperature increases, that average moves. But it also flattens out, which is very interesting, right? Because you got a lot of things in there moving at relatively slow paces and a lot moving at relatively high paces, velocities, when you're at 1,000 degrees. Different sizes, right, of particles at the same temperature are going to have different velocities, right? And those velocities are going to essentially increase as the particle gets smaller. All right, so just a quick review of the kinetic molecular theory. Right, it explains a bunch of properties of gases, and it explains that when gas particles collide with the walls, they exert some kind of force. This is pressure. Increasing the temperature of a gas increases the kinetic energy. That also then increases pressure. Decreasing the volume container means that you have more collisions, frequency of collisions, and thus the gas pressure is going to increase. If you want to maintain a constant frequency of collisions and a constant pressure, when the volume of a container increases, then those particles have to move faster. We can increase the temperature, right? And then increasing the number of particles in a container with a constant temperature and pressure and volume will increase the number of collisions and thus the pressure of the gas. All right, so that's it for the first section of Chapter 9, and that is all about gases.